All right, so I lied a little bit, sorry, when I said there was only one more. So I have to do another module, okay? So we have this formula, the half-life formula, which you could write in either of these two different ways that I point out here. And so we need to calculate the half-life for this reaction. So we're going to use that formula, T1 half is 0.693 over the K. And remembering this is activity 6 that we started on a while back, and the K is 0.0320 inverse seconds. So just take 0.693 divided by, notice the units are going to be the reciprocal of inverse seconds, or seconds, which is very nice because that makes sense. Okay, so the half-life is 21.7 seconds. Now it says, how long would it take for the concentration of A to decrease from 0.6 to 0.075 molar? And it says to figure out how many half-lives this is. So what you need to remember is every time the concentration decreases by half, it means a half-life has passed. So in 21.7 seconds, it'll go from 0.6 to 0.3 molar. Another half-life, or 21.7 more seconds pass, it'll go down to half of 0.3, which is 0.15. And then in another half-life, another 21.7 seconds more, it'll go down to half of this, which is 0.075 molar. And that's what we want. So basically, the answer is 3 half-lives to get from 0.6 to 0.075 molar. Now, the numbers don't always work out so nice, okay? But you can always solve the problem a different way. By the way, let's multiply this by 6 to finish the problem. And you get 65.1 seconds. So you could also do this problem using the formula, this equation that I derived for you a little bit earlier. I'm going to use this one here. Let me recopy it. What's going on? It's kind of slow, kind of delayed. Okay, so the log of A would be, well, the A here would be 0.075. A0 would be 0.6. So the log of 0.075 over 0.6 is minus KT. So let's calculate what this is first. 0.075 divided by 0.6 is 0.125. So the log of 0.125, which is negative 2.0794. I'm keeping a lot of figures. I don't want round off error. Is minus KT. So we know what K is. I'm going to divide both sides by minus K. So then the T will be, well, let's get rid of the negative signs. You can cancel them. All right, so if you do the math here, guess what? You get 65 seconds, which is almost the same. You know, you should get exactly the same answer. Well, these are close enough. So if you have numbers that don't work out, like let's suppose you can't just divide the initial number by half and by half and by half. Like let's suppose I asked you, well, how long will it take for the concentration to be 0.09? Well, you're not going to get there by half-lives, so you can always solve the problem this way, using this formula here. Okay, so here it says, if you know the concentration of A at 10 seconds is 0.436 molar, we did that earlier. What is the concentration of A 21.7 seconds after that? Well, you have to recognize that since we just calculated it, the half-life is 21.7. So 21.7 seconds after it's 0.436, it's going to be 0.436 divided by 2, or 0.218 molar, okay? Because a half-life has passed, 0.436 in a time t1 half, or 21.7 seconds, it'll go to 0.436 over 2, or 0.218, okay? So here's another problem. It's a reaction of this cyclical carbon, this 3-carbon cyclical compound. Carbons are bonded together in a ring. And so you go from cyclopropane to propene. There's a double bond there. That's why this is propene and not propane, which you'll learn more about when you take organic chemistry. So here is the first order rate law. The only time we can figure out what concentration is as a function of time is for first order, so it has to be first order. And this problem here I'm not going to do right now because this is just like what we did in activity 6, where you have an initial concentration and what is the concentration after a certain time passes. We did lots of problems like that. So instead, I'm going to go on to part B. So here's a problem like the one we just did. If the initial concentration is 6 molar, at what time, so we're trying to figure out what the time is, will it become 0.15 molar? And here we're using the equation that I used before, except we're putting in a C for A, since C is the reactant. Okay, so what I'll do is plug in these numbers, the log of 6. Well, I don't need to put brackets, it's just over 0.15 equals minus KT. So let's first figure out what this is. That's the log of 40. Natural log. 3.689. Then I'm going to divide both sides. You see, we're given K. Okay. I'm going to divide both sides by minus K. So we cancel these out. So the time will be 3.689. Oh yeah, I reversed these numbers. So this comes out to the log of 1/40th instead, a log of 0.025, which is negative 3.689. So I could tell I was getting the wrong answer because I would have had a negative time, and that just doesn't make sense. So I have to divide by K. 3.689 divided by, it comes out to 0.401. Okay, so that's how you do that sort of problem. And then what is the half-life of this reaction? Oh, the reaction takes place at 1,000, so that's not really relevant to the question. So the T1 half is 0.693 over K. And that comes out to 0.0753 seconds. Not very fast, not very long at all. So it's got a faster rate constant in this problem than the rate constant we used that was 0.032, and so we have a much shorter half-life. And then finally, part D, if the initial concentration is 10 molar, when will the concentration fall to 1.25? And here is a case where you can have everything. So what I'm doing here is I divide this by 2, then I divide it by 2 again. And each time, the time that elapses is a half-life. And so sometimes when the numbers work out, this is pretty easy, and you end up with 3 half-lives. And since the half-life is 0.0753, this comes out to 0.225 seconds. Okay, so that's pretty fast. All right. Okay, so that's all I have to say about this, and I'll post up some problems that you should do on this part of the unit.